Hello everyone. In the last video, we have discussed that the reuse factor is the number of cells in a repeatedness pattern in a cellular system. In this video, we will see a relationship between the reuse factor, the reuse distance, and the cell radius. In this video, we will also see what are the valid cluster sizes that can be used in cellular system, and we will also learn how to draw the different frequency reuse patterns. So let us begin our discussion with few definitions. Let us first define co-channel cell. Co-channel cells are the cells with the same frequency band. So in this example, we can see this particular cell, that is cell 1, and this particular cell 1 are using same band of frequency. Similarly, this particular cell and this particular cell, that is cell number 2, are using same band of frequency. So that is why these cells are all will be known as co-channel cells. Let us denote the distance between the co-channel cells as d. That means the distance between this one and this cell will be equal to d. Similarly, this distance again will be equal to d. That means the distance between all co-channel cells will be equal to d. Similarly, the distance between this cell 2, between these two, all 2 will be equal to capital D. Let us denote the distance between the adjacent cells as small d. So the distance between this adjacent cell will be denoted as small d. So distance between this 1 and 2 will be small d. So all adjacent cell distances will be denoted by small d. Let us represent I as the move along the hexagonal sides and j as the move at a 60-degree anticlockwise turn with respect to the hexagonal sides. To understand this, let us first see the Cartesian coordinate system. Let us consider a point I, j in a Cartesian coordinate system. Now to locate this point with respect to the reference point, we move I distance along the x-axis and we take a 90-degree anticlockwise turn and move j distance, and this is how we can locate this coordinate. In a hexagonal plot, to locate a particular coordinate ij, we move I distance along the sides. The distance between the centers of a neighboring cell is considered as 1i, and if we move two cells, then it will be 2i. Similarly, if we move up to 3 cells, then it will be 3i. Now we have to take a 60-degree anticlockwise turn and we can move along this direction, and this is our j move. So in a hexagonal coordinate, let us consider I equal to say 1, j equal to say 1. Now let us find the relative coordinate from this cell to a cell with a distance represented by I equal to 1 and j equal to 1. Now since I equal to 1, so here there will be one move, that means from one cell to the next cell, that is I equal to 1. Now we will take a 60-degree anticlockwise turn and we will have one move, that is j equal to 1. Now let us consider another cell with I equal to 1 and j equal to, if we start from this cell, this particular cell, along this side, one move and take a 60 degree anti-clockwise turn. So this is I equal to 1 and j equal to 1. Now let us consider I equal to say 2, j equal to 3. Now let us consider any one cell. So here let us consider this cell. So here I equal to 2. So along the sides we have to move 2 cells. So this is one move, I equal to 1, and this is another move, so I equal to 2, and we'll take a 60 degree turn, anti-clockwise turn, and we'll move in this direction. So this is I equal to 1, sorry, j equal to 1, j equal to 2, and here we'll have one more cell like this. So here also, so this is j equal to 2 and this is j equal to 3. So let us consider I equal to 3, j equal to 1. Now let us consider this cell. So here I equal to 3, so along this side, that means we can move in any one of the side of the 6 sides. So I equal to 3, so we'll move up to 3 cells, one cell, this is cell 2 and this is cell 3. So here I equal to 1, I equal to 2, I equal to 3, and we'll take a 60 degree anti-clockwise turn and move on that along that side. So this is j equal to 1. So this is how we can select the relative distance between two cells in a hexagonal coordinate. Let us determine a relationship between the distance between the neighboring cells d, that is small d, and the radius of a cell. So let us consider this cell. So here this distance is considered as small d and the radius of the cell is r. So since this is a regular hexagon, so the sides of the hexagon will be also equal to r. So that is why this distance will be r by 2. Now if we consider this triangle ABC, we can write AC square is equal to BC square plus AB square. We can replace AC with R and BC as R by 2 and AB as D by 2. So this implies a relationship between R and small d as d equal to root 3 r. Now let us consider the cosenal cells A and C. Let us define the distance between the center of the cosenal cells A and C as d, which is the reuse distance. So capital D is the reuse distance. Now to locate C from A, hexagonal coordinates are used. So therefore, AB can be written as ID. So that means it's a move along the sides of the hexagon. So if we have one move, AB will be equal to 1D. If we have two move along the sides, it will be AB will be equal to 2D. If we have three move, AB will be equal to 3D, like that. And BC is the move along the 60-degree anti-clockwise turn with respect to the side of the hexagon. So it will be represented by JD. Now let us apply the cosine law at the angle ABC of the triangle ABC. So you can write 2AB dot BC dot cos of ABC is equal to AB square plus BC square minus AC square. So this is as per cosine law. Now we can replace AB with ID. So AB you can replace ID and BC with JD and AC with capital D. So you can replace this ID, JD, cos of ABC. Now you can write 2I D. You can write 2IJ D square. Cos of ABC, the angle ABC will be 120 degree. From hexagonal geometry you can find it will be 120 degree. So you can write cos 120 degree equal to I square plus J square small d square minus capital D square. So this, if you simplify, you can write I square plus J square plus I J is equal to capital D square by small d square. And this part is represented as n, which is the reuse factor. So therefore you can write n is equal to capital D square by small d square, which implies capital D by small d is equal to square root of n. We can also write capital D by r is equal to square root of 3n. Now let us see what are the possible values of n, that is the possible cluster sizes. If we consider I and j equal to 0, that means n equal to 0, so in that case it has no meaning. Again, if we see the cluster size when I equal to 0 and j equal to 1, in that case n will be equal to 1. However, if we select that cluster size, that is n equal to 1, and it will represent the co-channels will be placed at the neighboring cells. So therefore there will be interference, so which will be an impractical situation. So therefore this cluster size or n equal to 1 is not possible. Now if we go on the other cluster sizes, we can see when I equal to 1 and j equal to 1, then the cluster size is 3. Cluster size is 3. So this is the smallest possible cluster size in cellular system. So accordingly we can see the other possible cluster sizes. Now let us learn how to draw a reuse pattern with reuse factor n equal to 3. For that, we need a hexagonal graph paper, or we can draw, initially we can draw the hexagonal cells like this. Now let us consider any one of the cell in the graph. Now since n equal to 3, therefore as per the previous table, you can see it is possible when I equal to 1 and j is equal to 1. Now we will try to draw a pattern with n equal to 3. Let us start from this cell. So since I equal to 1, so along the sides of the cell, if any one of the side, it has 6 sides, any one of the side we can consider, we can move a distance which is given by I equal to 1. Now we will take a 60-degree anti-clockwise turn. So this move will represent j equal to 1. If we place a frequency f1 in this particular cell, then we can place or we can repeat that frequency f1 in this cell. Similarly, we can continue along the other sides of the hexagonal cell. So this is from this cell to this cell, I equal to 1, and with a 60-degree turn, j equal to 1. So now in this particular cell we can place that frequency f1 here like this. Now let us complete the other cells. So this is I equal to 1 and this is j equal to 1. So this is f1. Similarly, in this side I equal to 1 and this is j equal to 1. So here I can place f1. So here I can place f1. Now the last side, so here we can place f1. So here you can see this frequency f1 can be placed in this cell, in this cell, this cell, this cell, here and here. So these all cells are known as coaxial cells. Since n equal to 3, so we will have 3 frequencies or 3 group of frequencies in a repetitious pattern. Now since one frequency f1 is placed, now we will try to place the next frequency f2 in other cells. So you can select any one of the empty cells where f1 is not placed. Let us place f2 here. In the same method, we will try to place the other f2 in the cells by using the reuse distance. Here you can see that this is along the side I equal to 1 and with a 60-degree turn anti-clockwise turn. So here I can place f2. Similarly, here f2. Similarly, so here f2 can be placed. The next side, here f2 can be placed. The next side, here f2 can be placed. Sorry, this side f2 can be placed. So here all f2 are being placed. Now the third frequency f3 we can place at the empty cells where f1 and f2 are not placed. So here I can place f3. Now by using the same reduced distance we can place the other f3. So here I can place f3, f3 like that. So in this drawing, we can see that this F1, F2 and F3 are one pattern. So here this is another pattern, this is another pattern, like that it has been repeated. So this is how we can draw a reuse pattern with n equal to 3. Now viewers can try to draw other reuse patterns. Thank you very much for watching.